All right. So the first one, you're given a system. It's written in a matrix form, but you're given a system. To start with, it's given you that system, right? So if you create your augmented matrix, what would be your first step in row reducing? Right. Good. Thank you. When you do that, and that's going to be your exact same first step in every single part, right? That's going to be the first step is multiply by -3 and add down, right? When you do that, you'll get lambda minus 6 here. So the whole crux of this whole problem is, what would your next step be? What do you want to see here? A 1, right? I want to see a 1 here next. In order to see a 1, what do you need to do to this row? Yeah, divide by this, right? In order to be able to see a 1, I need to be able to divide by this, right? When can you not divide by this? When lambda 6, right? That's when you can not divide by that, right? So what happens if lambda equals 6? What do you get? You get a 0 there, don't you? So how many solutions do you have if lambda equals 6? Yeah, infinitely many, right? Because we got that pivotless column there, don't we? So we get infinitely many solutions. So what happens if lambda is not equal to 6? Well, if lambda is not equal to 6, then what can you do again? Divide by it, right? And what do you end up with? You get a pivot there, don't you? Oops. And so now how many solutions do you get? Yes? It applies to all numbers that are not equal to 6. Yep. As long as it's not equal to 6, it's not 0, so I can divide by it. That's what we're looking for, is when can you divide by it and when can't you divide by it, essentially, right? So in this case, how many solutions do you get? Yeah, you get exactly 1, right? Oops. So when you do the other parts, it's just a matter of paying attention to what's going on in the column, the constant column, right? So I believe in the first part, or sorry, the second part, you had that one. And then notice if you multiply by -3 and add, multiply with the first row by -3 and add, you get that again, don't you? Essentially the same thing, except you got a 1 up there. So now, same scenario. Your next step would be to try to get a 1 here. When can't you get when can you not get a 1 there? When lambda equals 6. If lambda equals a 6, you get a row of 0. So how many solutions do you get? Infinitely many. If you can divide by it, you get exactly 1. And then there's no way for you to get no solution, because it's going to be consistent either way. And if you do the third one, you'll end up with a constant other than 0 there. So then you can't get infinitely many, and you'll get no solution if lambda is equal to 6. So it's just a matter of playing around when you can divide by that particular constant. Other question? Matt.
How do you say, like, just because lambda does not equal 6, how do you know for sure that bottom one's going to be a 1?
Well, if lambda is not equal to 6, then your row operation is do 1 over lambda minus 6 times row 2 and replace row 2. So it doesn't matter what lambda is. As long as it's not 6, I can divide by the number. So then I just divide by the number. Other question? No, I'll just stay away in the office. Thank you. All right. Again, I will ask, I've mentioned this before, some of you came in, please do your homework on a separate sheet. I cannot tell you how annoying it is to create it when it's on the same sheet as I hand out. And one thing you don't want me to do is annoyed when I grade, right? All right. All right, new stuff today. Start doing some operations with matrices. We've already talked about using matrices. Yeah, talk about using matrices to do help us solve systems of equations and keep track of information. So there's going to be other instances when we'll want to keep track of information with matrices, but there will be also things that we'll want to do as we are applying systems of linear equations ideas to future things. So some of those operations we'll want to do are standard arithmetic operations. Before we get to that, though, we want to talk about some ways that we can define matrices, some ways that we'll notate matrices, those kinds of things. So some conventions that we'll do, some standard matrix notations that we'll do. We use, and I think we've already seen this a little bit, we use capital letters to denote a matrix. The one exception to that is if we have a single row or we have a single column. So maybe your matrix is 1 by n or m by 1. If we've got 1 row and n columns or m rows in 1 column, then we might use a vector notation. Usually your vector notation is written as a small letter in boldface, but of course it's hard to write boldface on without scribbling, essentially. So we'll put a little arrow over the top, and I'm lazy, so I do it in one motion. I don't bother putting the other part of my arrow on there. So those are arrows over the top. Okay. So if it looks like a vector, then we might write it as a vector, and later on we'll probably treat it as a vector. So we'll kind of the whole point. Just to make sure that we're all on the same page with standard notations. Another thing that we've talked about a little bit is how you refer to the entry of a matrix. So as a general form of a matrix, looking at their entries, you might write a matrix in a general form in this way. Say that the little entry here, or sorry, the little letter, the smaller case letter, lowercase letter, here is representing the entry of a matrix. That's the same as what the capital letters were referring to. And then again, our subscript here is telling you row number and column number. If you want to get super duper technical and want to make sure that you've got the dimensions labeled as well, you might see a little subscript outside of that general entry notation with an m by n. So this is just standard notation around brackets to talk about it as general entry. We typically use these if we want to try to describe what the entries look like in a formula, or if we're trying to prove general properties of matrix arithmetic, which we'll see in a little bit. All right. Another way you might write it is just actually try to write out the entries, generally speaking. So maybe you'll start with an A11, an A12, go out to A1N. Oops, it's an N. The next one would be A21, A22, go out to A2N, continue down to the mth row. So writing it as some sort of general array, if you will, and using the dots to say that things are continuing on there. All right. Again, the whole reason why we're going through all of that is just to denote here, or sorry, just make sure that we're all on the same page with the same notation all the way through. All right. So along those same lines, let's start doing some definitions using our general entries. The first one, I know it seems a little silly why we want to define when two matrices are equal, because hopefully it's fairly obvious when they're equal. But the whole idea of this particular section is define some arithmetic properties and then prove some properties of the arithmetic as we're going through in the next section. So to be able to prove properties of arithmetic, like for example, you can add in either order or maybe multiplication distributes over a sum, you'll want to understand what we mean by equality of matrices because we want to show that the entries themselves all match up. So that's why we're defining what equality of matrices is. So we already know that two matrices are going to be equal if all their entries match up. So we just say that the A sub ij is equal to B sub ij, and this has to be true for all I that runs down the rows and all j's that run across the columns. So if I think of my matrix A and B as being m by n matrices, well, they better have the same dimensions if they're going to be equal, right? So I probably should write that down as well. But we want to make sure that all of the entries are the same. So the I runs down your rows. And if I think about these as being m by n matrices, then my rows are going to go from 1, 2, 3 down to m. And my columns, if I said m by n matrix, will go from 1 to n across. So the only way that the matrices can be equal is if all of their entries are equal. And of course, the only way that can happen to even start with is if they have the same dimension. All right. This is a quick example of this. If I want to solve this matrix equation, yep, that's right. Hold on. Yep, that's right. If I want to solve this matrix equation, how are we going to do that? What do we need to do? Say it again. Okay, so what would be the first thing we would want to balance, if you will? Yeah, I have to have 3a equals a minus 6, right? Those upper left entries have to match. What else has to be true? Okay, b minus 6 equals 2b.
2c plus b equals 0.
Minus 4d equals 16.
Good. And these should be fairly straightforward to solve. This one, you'll get what? A equals negative 3. This one, you'll get b equals negative 6. This one I'll do first. This gives me d equals negative 4. So that means my c must be 2. I did all my arithmetic right. So notice basically we're setting up a system of equations with this, though this particular system of equations was pretty straightforward to solve, since we only had, the only one that had multiple variables in the same equation was the third one. The other one made it pretty pretty easy to solve those individual numbers. And okay? All right, so let's talk then about how we can start doing some arithmetic, because again, the goal here is to do some arithmetic, and then the next section we'll start doing some proving of arithmetic properties. So the first arithmetic properties we're going to talk about are adding and subtracting, and then multiplying a matrix by a constant. And if you've done things with vectors, you're probably pretty comfortable with how these operations work. How would you like to add two matrices together? What would you like to do if you wanted to add two matrices together? Yeah, just add the corresponding elements together, right? So if you do that with adding, you do the same thing with subtracting, much like if you've done vector addition, right? Just match up your core entries and add or subtract there, right? So in particular, if I write this as some general entry, I'll call it C sub ij. And the reason why I'm doing it this way is we're going to prove some properties later that will help us show that that the properties are the same. Remember, we want to show that the two matrices are equal. I want to show that their general entries are the same. So I'll start by giving it a new name and then show how that the particular entry has to be defined. So the entries in A plus B have to be the sum of the entries of A and B corresponding in the same spots. What has to be true in order to be able to do this? What better be true about A and B in order to be able to do it? They have the same dimensions, right? I need to make sure all the spots all match, right? And this is going to be provided A and B have the same dimensions. So if they don't have the same dimensions, the operation is just undefined. Well, if when we add corresponding entries, what do you think we do when we subtract? Yeah, just subtract the corresponding entries. Good. So instead of plus, I'll have minus. Again, in order to make sure that we can match up our entries, we better make sure that these matrices have the same dimensions again. What do you think we're going to do with that constant? Now you got to think about, if you've done things with vectors, think about it in the same way. What do you think we're going to do if I do a constant times a matrix? What do you think we're going to do with the constant? Multiply to every entry. Good. I'll use a different letter here since I've got C for my constant. I'll use D sub ij. So I'll multiply every single entry by that same constant. Any dimension restriction on that, or can I do that for any matrix? I can do it for any matrix, right? It doesn't matter what the matrix is. So I can do that for absolutely anything. All right, so let's practice with some of these. Got a nice example here below. First example says, what do you get when you add A and D together? Why? Good. Undefined. Good. A is 2 by 3, while our D is 2 by 2. So the dimensions don't match, so I can't add those two things together. Does that make sense? Not too bad, right? They literally don't have the same size. Yeah. Yep. Nope, can't put in zeros. That doesn't work. That changes the matrix. Yep. Okay. Because then I wouldn't know, do I want to put when I make it the same size as the bigger one or the smaller one, I wouldn't know which one to define it as. So it's just an undefined operation in this case. What if we do A times B, or not A times B, A plus B? What do we end up with? What's the upper left entry going to be? In the next one over, in the next one, 1. Go down the next row. Good. Just adding the corresponding entries. Our answer has the same dimension as the two original matrices did, the two that we added together. Is that okay? Next one, 3 times C.
6, negative 3, 0, 18, negative 9, and 6.
Good. Yep, I agree. Is that okay? Not too bad. This last one here, we've got E plus 3F. You'll want to do the same thing that you do with order of operations. We'll do the constant multiplication first and then add. So I would probably just do this in steps. Your E is 4 negative 3. And what is your 3 times F going to be?
27.
Good. And then when we add, what do we get?
31.
Good. We okay with that? Okay. All right. So let's look at this last part. It's talking about solving a matrix equation when I isolate the x. Notice that our operations here are doing addition and scalar multiplication. So better make sure that all of our dimensions match up before even trying to solve it. A is what type of matrix for dimension? 2 by 3. B is 2 by 3. So it looks like we'll be okay with doing all our addition and subtraction operations, right? I would first just isolate the x like you typically would back in Algebra 1 class when you're trying to solve for the x, and then do the answer at the end, rather than putting in the individual pieces to start with. Okay. So the first thing you would do is what? Subtract the a, good. Right? And then to get x by itself, we would divide by 2. I'll write it as multiplication by a half to start with. So notice that this would tell me to first take 4 times b, then subtract the a, and then multiply every entry by a half. Right? Okay. You know, I can get back up to where my a and my b are. So, don't remember what it said now. Oh, let's move it off here this way. So A is -2, 1, 3, 4, 0, -1, and the B is 4, 1, -2, 5, -1, 3. Didn't leave a lot of space here. That's all right. First thing we'll do is what on the inside? Multiply by the 4, right? 16, 4, -8, 20, -4, 12. Then subtract. 16 minus a -2 is 18. 4 minus 1 is 3. -8 minus 3 is -11. 20 minus 4 is 16. -4 minus 0 is -4. 12 minus 1 is 11. So I did all my arithmetic. Oh, yeah, it should. So it'd be 13 instead. Thank you. And then multiply your 1/2 through. Oops. That's okay? Your calculator will do all of these, of course, as well, all right? So if you put in your A, put in your B, you can use the different matrices to do the operation. As we go along. Your calculator will also give you an error if your matrices don't have the right dimensions to do the operations. It'll tell you there's a dimension error, as a matter of fact. So far, so good? All right. So we've talked about addition, subtraction, scalar multiplication. Now let's talk about actual multiplying two matrices together. And if you've done this before, this won't look foreign to you. But if we want to multiply A and B together and actually use those, use those matrices to do some computations later on, some applications, we're not going to do it in what we refer to as the obvious way, right? Remember, with addition, we just added the entries together, right? Subtraction, we subtracted the entries from each other. The obvious way would be multiply corresponding entries, right? And that's exactly what you do when you do a dot product of vectors. If you've done vectors before, it's a dot product, right? Okay. And there is a dot product of matrices as well. And there are applications of doing dot products of matrices, but that's not matrix multiplication. That's literally dot product, okay? So in order to multiply two matrices, we have to have a certain condition met first. The first thing that has to be met is that the number of columns in the first matrix and the number of rows in the second matrix have to match. Okay? We need n to be equal to p. We have to have the entries in the middle, the numbers in the middle, the dimensions in the middle match up to be able to do A times B. All right? Okay. So what do we end up with when we do these dimensions? And we're going to talk about how we do this here in a second. What do we end up when we're done? Well, we end up with, the m by the k. We end up with the same number of rows in the first matrix and the same number of columns in the second matrix. That's how it ends up. So how do we end up doing this? I'm going to write it with letters to start with, and then we will talk about actually doing with some computations. So here's how you do the general entry. It actually is going to be a sum of products of things. So the ij entry is going to be a sum. Again, I'm assuming my n is my middle condition, if you will, my middle dimension. What we're going to do, notice that my column number here is changing, right? I would remember your summation notation, you plug in 1, then you plug in 2, then you plug in 3 and keep going, right? My column number is changing for the first one. So that means I'm running across a row, right? As the column number changes, you're going across the row. In the second one, your row number is changing. So I'm running down the column. So what we're doing is we're matching up the ith row with the jth column and doing this basically a dot product. If you've done dot products before, it's exactly what you're doing. You're dotting a row with a column. That's why we have to have the dimensions in the middle match, right? As I run down the row, as I run around across the column of the first, I'm running down the row of the second. Right? So I need those things to match. Okay. All right, so this is how you do it. So let's do a couple of examples, make sure we're understanding how that works. So I want to do b times c here. First, what's the dimension of b times c? What's the dimension of b to start with? 2 by 3, and c is a 3 by 2, right? This is 2 by 3. This is 3 by 2. Can I multiply those together? Do the numbers in the middle match? Good. Okay, so those match, so we're done. Or not done, but we can do it. Okay. What size, what dimensions is b times c going to have? It's going to be a 2 by 2, right? So b times c will be a 2 by 2. Okay. So let's talk about how we get those entries. I'll write it out longhand. I'm hoping eventually you'll get comfortable with it and you won't have to write it all out, all the products out all the time. But again, we want to get the row 1. You don't have to write these numbers on the outside. I'm just doing it to show how this works. I want row 1, column 1 entry of b times c. To get the row 1, column 1 entry, I'm going to use row 1 of b, column 1 of c, and match them together. That's how I get the 1, 1 entry. Okay? And then we basically do it, if you're familiar with dot product, we do a dot product of those two vectors. Okay? We'll do 4 times 2, 1 times 0, 3 times negative 3, and add that together. 4 times 2, 1 times 0. Oh, it's negative 2 times negative 3. I looked at the wrong row. My bad. I saw a shocked look on Trace's face. I did something wrong. I looked back up and realized I grabbed the wrong row. 4 times 2, 1 times 0, negative 2 times negative 3. Mentally, although I didn't do it just a minute ago, mentally I imagine just taking, personally, I think about taking this row and just turning it 90 degrees and matching them up. What would be your next entry? To the right. I want row 1, column 2. So which row and which column am I interested in? First row of B, and second one of C. The second column of C, right? Okay. So what dot product essentially are you gonna do? 4 times -1, 1 times 6, -2 times 2. I did not leave myself enough room. I thought I moved it over enough, but shockingly enough, I did not. Do we see where those numbers are coming from? Again, you can think about doing it a little bit more systematically, if you will, right? I'm taking the first row, and I'm going to run it through each of the columns of my second matrix, and that's how I'm getting my first row. And then do the same thing with the second row, run it through each of the columns to get the second row of the product. And just keep your working way down. If you do it systematically, you won't get it messed up, I think, as easily. All right, so how do we get the 2-1 entry then? Well, I'm going to take row 2 and match it with column 1 here, right? What are you going to multiply together to get that? Say it again.
I thought I was looking at from.
Oh.
And then 3 times -3.
Good. Then finally, the last one, we'll look at the second column. What do we get for that one?
5 times -1 plus -1 times 6 plus 3 times 2.
Good. Everybody see where those are coming from? Yep. And then we just simplify our arithmetic when we're done. 8 plus 0 plus 6 is 14. -4 plus 6 is 2. Minus 4 is -2. 10 minus 9 is 1. -5, -11, -5 when I'm done. We okay with how this is defined? Okay. All right. Let's do the next one. Can we do C times B? Yeah, we can do it the other way around, can't we? Notice that if we do C times B, we would switch things around. We still have these two things are matching, don't they? No problem there. But what size matrix are you going to get when you're done? A 3 by 3. So first question, does the order matter when you multiply matrices? Sure does. Those cannot be equal. They don't have the same size. So that's weird compared to other things that you multiply, right? Usually when you multiply other things, it doesn't matter the order that you multiply them in. For matrices, it matters. Okay? All right. I'm going to write them down here just so that I can... 2. So I'll get a 3 by 3 when we're done. What's the upper left entry going to be?
Expanded out.
You can just say it if you want.
3.
3? And how did you get the 3?
2 times 4 plus -1 times 5.
Good. 2 times 4 is 8. -1 times 5 is -5. Subtract, we get 3. Next one over is going to be... I think it's 3, isn't it? 2 times 1 and -1 times -1.
Oh, yeah.
Okay. And the next one over will be... -7. Do we see where those numbers are coming from? I can go through them step by step, but do we see where they're coming from? I don't want to take a lot of time to write things down if you're all seeing it. Is... No, maybe. Yes? Okay. All right, next one. Next row.
-6.
That one was pretty easy to do, right? Because the 0 is going to knock out the first row, isn't it? When you multiply the zeros, it knocks out the first row, so you had to multiply the second row by 6. Next one.
-2, -5, and 12.
All right. All right. This last one here, d squared. Well, your d is 2 - 416. What do you think squared means? Multiply it by itself. Good. So I will multiply it by itself, but we'll use matrix multiplication to do it, right? So personally, I think it helps to actually write it down, split it out as the matrix times itself. Because again, I'm pretty in my brain, I'm pretty visual about how I multiply together. Okay, so even though I don't usually visualize things very well personally, for matrix multiplication, I do really like to think about taking the row and flipping it. All right. Notice a 2 by 2 to be times a 2 by 2, and I get a 2 by 2. In particular, if you're going to square a matrix, what better be true about the dimensions? They better be the same rows and columns, right? We actually refer to that as a square matrix when you have rows and columns and numbers being the same. Okay. So it better be a square matrix before you can square it. Okay. All right. What do you get for the upper left?
0.
And then the next one over. Okay. And then 8 and then 32. Yeah, it has to be a square matrix before you can square it or do any power. Yeah, it has to be square to start with.
Is there a pattern with square matrices?
Is there a pattern as far as what?
Like how it's like -32, 32, and 8. Like they're all.
There's not really any pattern. It's just the way the numbers were in there. Yeah, actually, you just have to kind of do it.
Is it a 1 by 1 square matrix?
1 by 1 is technically a square matrix. Yeah. Yep. Is that right? So I'll leave the next ones there for practice. There's lots of practice in there, but you should be able to practice those and make sure you can do them. So let's skip a couple of pages and talk about how we can rewrite a system of equations in what we refer to as matrix form. So notice in this one we've got 2 equations and 2 unknowns. And it's asking us to write it as a matrix product, if you will, on the left-hand side. So we talked a little bit about how we created augmented matrices, obviously more than a little bit. We've talked a lot about creating augmented matrices. We talked very briefly about how we could create the coefficient matrix, right? When you leave the augmented part off. That's exactly what this A here is going to represent, is that coefficient matrix. So if I write that down first, that would be your A. Your X here, notice it's bolded. You know, it doesn't show it very well on the screen. It's bolded on your paper, right? And again, I mentioned to you that when we have bolded things, we think of those as vectors, and usually it's going to be either a column or a row, right? If I want this to be a vector, I'm going to point at this one even though I'm working up there. I want to point at if I want this to be a vector and I want this product to be defined, do you think I want a row vector? A 1 by something? Or do you think I want a column vector, a something by 1? It better be a column, right? Because if I do a row vector here, unless I only have 1 column here, I'm not going to have a defined product, right? So what I have here better be a column vector. What do you think needs, in this particular instance, what do you think needs to go on the column to get these expressions on the left-hand side of the equation? I better be an x here and a y here, right? And notice that works out, doesn't it? I get negative x plus 3y when I do the product, don't I? Yeah.
Oh,
Yeah. And then I get 5x minus 14y on the other one. So what do you think needs to be on the right-hand side? Well, it better be another column vector and make sure that we understand why. Our coefficient matrix here is a 2 by 2. This is a 2 by 1. When we're done, what should the product dimensions be? 2 by 1 again, right? So it better be a column vector when we're done. What do you think should go in that column vector? The constants, right? The 6 and the negative 2. Yeah, that's exactly right. So this is writing a system of linear equations in a matrix form. Okay. Now, in this particular case, if you're trying to solve this system, you want to isolate the x and the y, all right? So one thing that might be nice to be able to do is, quote unquote, divide this to the other side like you do in algebra class, right? But we never divide by matrix, but we do something that is equivalent to dividing, which is kind of multiplying by the reciprocal, right? Multiplying by a multiplicative inverse. So one of the things we're going to concentrate on later is figuring out when a matrix has an inverse. We'll talk about that later. But this is one of the reasons why we might want to write this in a matrix or as a matrix equation to try to solve. So on the next part, how will we write this in matrix form? What's going to be the A piece here? Okay. Good. Yeah, we're just taking the coefficients off of each variable in each equation, right? So the first row, we're just using the coefficients of the variables on the first equation and so on down the line. What's going to be your column vector next to it? X1, X2, X3, good. And then finally, the right-hand side, 1, negative 3, 0. Good. That okay? That's literally all this part is just writing it in matrix form. That's all there is to it. That okay? All right. So let's briefly look at an application problem. I'll skip the next one because you all seem incredibly bored by doing that. So we'll do a different type of problem here. All right. So let's talk about an application problem here. We've got a food company that has 4 different sizes of tomato sauce and tomato paste. One of them gives you ounces for each of the cans. The other one tells you how many cans of each sauce and paste are made each day. And then it asks you to calculate the product and interpret the entries. Okay, first, notice it says calculate the product AB. Could you do the product BA? No. Sizes aren't right? The only product we can do is AB. When we do AB, what size matrix did you end up with? A 1 by 2, right? A has 1 row, B has 2 columns. So you need to end up with a 1 by 2 when you're done, right? Okay. So if I do AB, I'm going to get a 1 by 2. I'll write it a little bit more expanded so that we can see the arithmetic. What's going to be your first entry? Expanded out. What's the first entry going to be?
6 times 2,000.
Okay.
Plus 10 times 3,000.
Okay.
Plus 14 times 2,500.
Okay.
Plus 28 times 1,000.
Good. Didn't leave myself much room. Now, when I move to the next entry, some of those numbers will change and some will stay the same. Which numbers will stay the same? As what we just did in the first entry. What numbers will stay the same? The first number, right? Because we haven't changed the row, correct? We're still using the same row as we did before, right? So we're still going to have 6 times something, 10 times something, 14 times something, and 20 times something, 28 times something, sorry. We're just going to multiply it by the second column, right? So we'll get 6 times 2,500, 10 times 1,500, 14 times 1,000, and 28 times 500, and I didn't leave myself enough room again. Anybody happen to type those numbers in? Oh, let's see. 12 and it's like I can do it in my head. I don't really want to.
Oh, it's right now.
I think it's 105,000.
Okay. Okay, and
I was doing it in my head.
oh, you're doing your head. Oh, what is it? That's 12,000. That's 30,000. That's 94. Okay, well we got two with 105,000. Okay, what's the other one?
I got 58,000. Yeah.
58. Okay. Doesn't matter. I'll call those numbers good. It doesn't really does not matter what the numbers are. The second part is as long as you understand how we're computing them, right? The second part says interpret the entries. What do the entries mean in this scenario? Yeah.
Total number of ounces
For
the sauce.
good. So this is telling us that the company produced 105,000 ounces of sauce per day and 58,000 ounces of paste per day. Right? Because you're doing number of cans of sauce times number of ounces of sauce, essentially. So it's just a quick way to keep track of all those things. Questions on that at all? All right. So we defined our operations. So next time what we'll concentrate on is proving some properties of arithmetic. So we'll get into section 2.2 tomorrow or Wednesday, whatever day that is. Have a good one. We will see you then.